So we're talking about our differential equations today, and we've got kind of 5-6 types of problems, right? Verify a solution, I guess, was 7-1. Maybe that's only one problem there.
Hey, Professor, you sharing your screen?
Not yet. Thank you, Josh. Forgot I turned it off. So verify a solution we talked about already. It's pretty easy. In 7.2, we're going to estimate a general solution or a family of solutions using a slope field. Slope fields are very cool. Kind of like a magnetic field or water flow. I like water flow. Like electricity is like water flow. You can see where all the water, the caverns it has kind of carved out type of thing. We're going to use GeoGebra for that. So I'll ask some of you to be looking at GeoGebra with me at the same time. So that's one thing. I like to be able to find the answer in 7.3 to bring it into these slope fields so you can see what it looks like in a slope field. So of course we're going to have a general solution, and then we're going to have an initial value solution, right? So what's the difference between a general solution and an initial value solution? In the general solution, when I integrate, I get a constant of integration. And that number, whether it be a C or a K or an A, whatever letter we use, can be randomized, right? And it will give me a different curve every time, right? It might just be the same curve shifted, right? But it might actually change the curve. And when I have an initial value solution, I'm trying to find that constant of integration. Does that make sense to everybody? Like if I integrate e to the x dx, I get e to the x plus c, right? And so this is a general, right? And if I look at that e to the x plus c, it's this one and this one and this one. And it's all those curves, right? But if I say it's y equals e to the x plus 1, this is an initial value. So I've isolated what that c value is, right?
Does that mean that there's like only one correct c value?
If you're saying I want to land on the moon, yes, there's going to be one solution for us, most likely, kind of thing, right? If you want to say I just want to shoot this rocket out to space, I could shoot it in any direction, but if I don't start it on the right initial path, I'm never getting to the moon, kind of thing.
Okay.
Yeah. So in 7.2, we're going to be estimating general solutions and finding initial value solutions on a slope field. Okay. And then our next particular thing. So I'm just going to try and underline each of these. Right. Our next one is estimate a future value of an initial value solution using a numerical method by Leonhard Euler or Euler, I don't care what you say, by using Euler's method. There's some debate on how to say his name, but eulogy, we don't say eulogy, so. And he's dead, so we can't really ask him how he pronounces his name. But that one is really nerdy, super number specific stuff. So like Simpson's method, right? So it's not.
Don't they use this in is it physics, mechanical physics?
Oh yeah,
Or,
yeah. We're trying to find like derivatives are things changing, right? Like if you think of a position time curve, a derivative is your speed, and then your second derivative is your acceleration. So how is something changing in position? How is something changing by speed? How is something changing by acceleration? And then if I want all of these things to meet up, right? I want to get this particular satellite into a certain orbit, right? Then I've got to be able to kind of predict where it's going to go, so I can adjust so I can know how much fuel I need, so I can adjust, all kinds of little subtle things. Really cool stuff. That we are still pretty far away from in terms of our careers. So Ash is studying physics, interested in aerospace, right, Ash?
I want to go into experimental physics, but I haven't ruled out aerospace.
Okay, so yeah, but you're gonna dabble in all of them through your bachelor's degree and into your graduate degree, and then you'll find finally as a second year, third year graduate student, you'll find an advisor.
It sounds really interesting, but I know I was told not to get a focus, like a concentration in physics yet until my master's.
It's too early. Exactly. That's what I'm saying. Second year of your graduate program, you'll now have looked at every field and decide which one's the one for you. It'll pick you. You don't pick it. It's like a dog. Sometimes you can go look at a dog and it won't like you, and then sometimes you go look at a dog and you don't like it, and it's the one that it just connects, and then you're like, that's the dog for me.
Yeah, that's what I'm hoping.
Yeah. So that's 7.2. I think I'd like to get to most of 7.2 today, but I want to reach into 7.3 first, because it's nice to be able to solve problems instead of just talk about them abstractly. So 7.3, what we're talking about is finding solutions. So finding general and initial value solutions of separable equations. And so we're going to do that first because it's fun. At least it's fun to me, and it's the integration part, right? But then we're going to apply that into our slope field and apply it into our Euler's method. And there's two types of problems there. There's simple separable, and then there's U-subs. We won't do U-subs today. We'll save that till tomorrow. So finding solutions. And then lastly, our orthogonal families of solutions. So there it is. There's the rest of what we're doing. We will finish all that today and tomorrow. Wednesday we'll review for the midterm. Thursday is the midterm. None of Chapter 7 is on the midterm, right? None of Chapter 7 is on the midterm. And so, like I said, if you're really worried about the midterm, you're going to wait until this weekend to do anything in 7, okay? And you should be fine with that. Nice. So let's jump right into our 7.3 initial finding separable solutions, okay? So we're talking about here in 7.3 separable equations. And so when they're separable, so this is one of these early pieces of differential equations. This is like the first. So you know how we've been doing all these integration methods in differential equations. You're going to be doing all of these methods of solving differential equations or estimating them, right? So the things that we're doing today are your first 2 weeks of diffie-qs, right? And separate, right? Yeah, separate. Sorry, can't spell. Separable. Separate is how I used to remember how to spell that one. So separable equations. So what we're looking at is something super. Let's just start really simple. If I say y prime is e to the x, right? How do I find the solution? Well, it is very simple, but what our process is going to be, we're going to show the complicated process so that when we get to something really difficult, we can do that. So on this particular one, I'm going to rewrite y prime is dy dx. And if my functions and my factors are multiplied or divided, excuse me, then it's pretty much a separable equation. So everything should be either a product or a quotient in this case. So you see my dy over dx, and on the other side just a factor of e to the x. So everything here is a product or a quotient, separable. I'm thinking it could be separable. And so what I'm going to do is I'm going to isolate my two worlds here, right? And yes, cross multiplying, but you're putting your differential piece related to x's with the x functions, and you're putting your differential piece related to the y's with the functions of x, right? Does that make sense? So on the left-hand side, I have a 1 dy. Do you see that? I took a derivative of a y, and I got 1 dy. On the right-hand side, I have an e to the x dx. I took a derivative of e to the x to get the e to the x dx. So now I can integrate this, right? So now I can integrate. So I integrate. Sorry, let me use a different color there. I'm integrating here, and I've already got the differential built in, right? So I'm just saying, well, let's undo that differential, right? We just took a derivative. Let's undo that derivative. And so what do I get here on the left now? I get a y, and I get e to the x plus c, and there's my general solution. Pretty easy, right? Very, very easy. How about that? Very easy. Now, I will want to do something to get that c value fixed if I can, but nothing right now. Now let's look at a slope field here for this one, okay? Because this one's really easy. But let's look at a slope field for this one. So I'm going to GeoGebra, and I'll post this link today. GeoGebra will eat your RAM. If you leave it open and go get a snack or something and come back, your computer will probably be so sluggish, if not frozen. So just be careful of that, especially if you're like me and you have a very small brain, I mean in terms of the computer. So I'm going to GeoGebra, so like geometry and algebra put together, .org. Anybody here going with me now, just so I know? I'm making sure I'm not going too fast. Anybody going to GeoGebra right now? Why is no one talking to me today? Did I offend anybody or something? What the hell's going on? I always get nervous when no one's talking to me. Usually in my family, I've offended somebody. We start talking about religion or politics or something. And no one.
It's just Monday.
Oh, okay, it's the Slugfest Monday.
Yeah.
Yeah. It was a crazy weekend with Juneteenth and start of summer and Father's Day and
Yeah.
I don't know. It was.
I helped my sister this past weekend because she was doing an event for Juneteenth. She makes products.
Okay. Yeah.
So we were working an event.
Yeah. I bet there's a lot of partying in DC and celebrating, which is good. So I go to GeoGebra, and there's a little search engine here at the top right. So I'm going on that, and I'm going to slope fields. Now I would encourage you, I'm just searching for slope fields. I'm encouraging you to play around and find one. I do like, let me go back and put a space in there because I'm not seeing the one I like. I like, it might be Brzezinski. I thought it was, someone else. It might be Brzezinski. Let me just look real quick. Could be Steve Phelps. Oh no, here it is. No, that's not it. But it doesn't matter. This is the one that looks familiar to me. I want to be able to type in the equation, right? So you see here I have a text box for my equation of y prime. I want to be able to type in the equation. I want to be able to, I don't care too much about changing the length of the little hash mark. You see the red marks? But you can see here what I'm talking about is water flow. You can see that, you can see the path of maybe the Grand Canyon. Right? The water's carved out the canyon, right? And you can see the path there. And this particular path is crossing over an initial value. So if my initial value was here, right, you can see the path that water would be taking, or the electricity. They move in similar ways, right? So this is a slope field. I thought I used a Juan Carlos one, but you play around with it. This looks like it. So Martin may have stolen this, and then you can re-edit them and make them into your own and that type of thing. But I want to put in my initial value. Remember I had y prime equals e to the x, right? So no matter which one you find, you want to be able to put in your function. Okay. So once you separate things, you should be able to put in your, actually before you separate, you should be able to put things in. And so again, you can see the e to the x curve. If I say if x is 0, e to the 0 is 1. So I put in this initial value of 0, 1, and you can see e to the x. Right? Not that precise, but good enough, okay? Not super precise here. We know e to the x looks a little different than this, right? But it's getting us the general idea of where are the families. And you can see all the families that are just e to the x plus 5, e to the x plus 4, e to the x plus 3, right? You can see all of the families there. And this is, of course, I'm starting with a really super simple example, right? And of course they get complicated, okay? So when you're practicing finding solutions, go to slope fields, right? Go to your slope field, put an initial value in, go to your calculator, graph your solution, and see if they're matching up. And you'll see me do that in a second here, okay? But use these visuals to get yourself some understanding if you're getting it right. Now, I will give you a slope field in your test, in your final, and you will find the solution, but then you should be able to graph that solution on your calculator and see that it would be able to fit into the slope field, right? And even if you had to hand draw it, you should be able to see that. And I'll show you what I mean. So I'm going to be stupid and leave GeoGebra open just so I don't have to open it again, but it's going to wreak havoc on my page here, but that's okay. Let's do another problem a little bit more difficult, okay? So let's say y prime equals y e to the negative x. And so you can see on that right-hand side, I'm multiplying and dividing. I'm instantly thinking, okay, separable, right? I still, I believe I could get something not separable, even though I'm multiplying. Like if I think I had y to the x, e to the minus x, I probably can't do separable on that one. So, but in general, we're looking at if I'm multiplying and dividing, I'm thinking it's probably separable, or at least that's going to be my initial try, right? So here I get the dy dx equals y e to the minus x. And of course I get 1 over y dy equals e to the negative x dx. Everybody with me there? Make sure everybody's here with me. There's my initial problem. And let's make this an initial value problem. Let's say it's 0, 1. So as soon as I give you an initial value, a point, where I want the river to flow over, right? They're talking about initial value problem. So this whole piece would be given to you. Does that make sense? And so if I just give you a diffie-q, I'm asking for a general solution. If I give you an initial value, I'm asking for a general solution and an initial value solution. Okay? How are we doing here? Everybody waking up here? We're okay. David's okay. Charlie's okay. Only 2 cameras here. Charlene's got the thumbs up. How's Shen, Sarona, Ash, Adam? Thank you. Good morning. So this one I'm going to solve. Oh, more thumbs. Thank you. I always say they're missing a couple of symbols on this Zoom thing. You know, you should be able to give the teacher this one too, and not just, you know. It's a joke. You know, I get the, he's so rude. Rate my professors. He's rude. He's obnoxious. That's true. I'm from Jersey. What do you want? So now we're integrating both sides, right? So this is kind of step 4 when I'm putting in my integration. What do I get on the left?
ln of y.
Nice. Ln,
yeah,
ln of absolute value of y. Absolutely. And on the right, I get the opposite of e to the minus x plus some constant c. So I can go with my initial value now, or I can go later. In this particular one, it's not bad to go now, right? In this particular one, it's not horrible to go now. And so if I put in x is 0 and y is 1, right? What do I get for c? Do you see it already? At x equals 0 and y equals 1, what do I get? Ln of 1 equals e to the minus e to the 0 plus c. So I get c is 1, right? So sometimes putting that initial value in right away works. Sometimes it's better to stay a little bit later, and I'll do one like that next. Okay. And you'll see what I mean. Actually, maybe you won't, but maybe it doesn't matter. I have to think about that. If I can plug in, I should be able to plug in, right? So this is my general solution. But the problem is, here's my real thought. I want the general solution to be y equal, right? Y equal, and then there's a arbitrary constant in there. So in this particular case, I did it too early. I want to be able to come up with a general solution. So let me wait. I know the answer is 1, okay? I know the value for c at least is 1. But let me keep going with my general solution first, okay? So I want to solve this. I want to get rid of the ln, right? So I want to get rid of the ln. So what do I have to do to both sides? Raise it to base e, right? So I've got e to the ln of the absolute value of y equals e raised to the c minus e to the negative x. Oh, this one's nasty. This one's pretty nasty. So on the left, the e and the ln undo each other, and I get absolute value of y equals e to the c times e to the minus x. And we tend to do that as much as we can. We tend to kind of get the coefficients separated from the piece with the variables in it. So e to the c, which we know is already e to the 1, which is e. We already know that that's the leading coefficient here. But how do we get rid of absolute value? What's your gut instinct on that? How do I get rid of those? I remember I want y equal, right? So how do I get rid of the absolute value?
Inverse of y?
Say it again, Nima. I'm sorry.
The inverse of y?
Okay, so I like the thought. I think you're thinking of not the inverse, but we need the plus minus. We need the opposite, right? So we're just going to do that. We're going to take our plus minus. And so I can still see my value of c, but I really have this piece e to the c, right? I have this piece e to the c. I want to call that some new letter. Typically, the book will use a or k or something like that. So here's my general solution. Y equals plus or minus k, or just k, e to the minus e to the negative x. And then k, of course, is a real number, right? So plus minus, it could even be 0. It's not 0, right? When it's 0, it's really boring. And I also know it's an e to the c. E to the c can't be 0, right? But this is where we usually get to this general solution. Now, what do I want to do? I want to plug in. So this is my general solution. This is my general solution. It's not bad. You can still put the plus minus on here. That's fine. Right? Either way, plus or minus, because it's a k, it's either positive. If it's 5, it could be positive 5, it could be negative 5, right? If it's 0, it's positive 0, negative 0. It's not 0. In fact, we already know it's positive 1. But e to the c is 1. And so then e to the 1 is going to be e. So we think k is actually the number e. So this is our general solution. That's what we want to write. Okay? All right, so now, how are we doing here? Is this making sense?
So you just changed e to the c into k because there is no variable?
Exactly.
Yeah, okay.
Yeah, and the book you'll see the book will do that. They'll use k a lot for constant. It's a joke kind of thing, I think, a math joke. Constant with a k, right? Or they'll use some other letter, whatever letter they want. Sometimes an a here. Right, we're used to seeing this particular curve as y equals a e to the negative kx kind of thing. So a is that initial value. So from pre-calc, like when we did half-life and exponential decay and all of that stuff. So there's my general solution.
In the book, I read A.
Yeah, capital A, right?
Yeah,
capital A they use. You can use whatever you want. You have some freedom. Like George Foreman has 3 boys and they're all named George. It's real freedom. You can do whatever the hell you want. It's not a joke. It's true. So we're going to plug in our initial value, right? So 1 for y equals plus or minus k e to the minus e to the minus 0, right? So what do I get? I get e equals plus or minus k. So obviously k is e, right? Because the left side's positive. The right side has to be positive. So our initial value solution now is y equals e to the minus e to the negative x. What that looks like, I have no idea. I bet it's cool. It's probably cool or it's really ugly. It's usually what happens. Some of these things get crazy at 0, right? But the general idea is pretty simple, right? This whole concept is pretty simple. I am taking an initial value, splitting it into differentials of each variable I have, integrating, taking a look at that slope field to see all of the family of curves, and then finding an initial value and seeing if that hits exactly at that one particular river path on my slope field. So let's go to our slope field now. How are we doing? We okay? It's pretty easy, right? It's a nice break from volumes and all of that shell hell and disk and washer and all of that. So my initial thing is y e to the negative x. So I'm going to my my slope field here, and I'm putting in that y e to the minus x. And I hit enter. Not too exciting. And I've got my initial value set, right? I've got my initial value set. Pretty simple, right? You get the idea. And you can see all my family of curves look very similar, right? Nothing is really changing horribly here. But now I want to go to Desmos or your calculator, right? So running Desmos and GeoGebra at the same time. I'm really asking for trouble here. It's just running these scripts in the background all the time. That's why it's eating up the RAM. And I'm going to put in my initial value problem, which was y equals e times e raised to the, I forget already, minus e to the negative x, is that right? Minus e raised to the negative x.
That's right.
And the main thing that I want to see from my slope field, and why doesn't it like my other piece? Why doesn't it like my other piece? Maybe I made a mistake, but I'm really looking at the piece that's really close to the initial value. And it just didn't pick a good problem, but in my Desmos, where I'm close to that initial value, I'm looking for that particular curve. Why is Desmos giving me this down here? Because it's just, I'm sorry, why is GeoGebra doing that? Either I made a mistake, which is possible, but most likely GeoGebra just can't handle the calculation like Desmos can. The next one will be a better example, okay? Let me just make sure I didn't do anything here. Looks right. It's the calculation is sometimes way too crazy. So I'm gonna go with that answer, whether you believe me or not. It's okay. Let's do another one that will give us a little bit of a better solution here. So I like x squared over y. So y prime is x squared over y. This one will give us a much nicer solution. But you get the idea, right? Get the general solution. Look at the slope field for the general solution. See if you can see where the grooves would be. Find the initial value solution if given to you. Plot that on your calculator and see if my slope field is giving me the same result. So this is another example here. This one will work out a little bit nicer. So y prime is x squared over y. Now let's make it even easier. Let's just do x over y. Sorry, x over y. Nice and simple. So what do I get from here? Where do I go? I get y dy equals x dx. And I integrate, Make sure I'm not going too fast here. Everybody with me? Anybody need a moment? So on the left-hand side, I get y squared over 2. Right? On the right-hand side, I get x squared over 2 plus the constant c. Let's get rid of the 2 because we're solving for y. So I'm going to multiply everything by 2. And I get y squared equals x squared plus 2c. At this point, I could rename 2c anything I want. I could rename it c. I could rename it k. I could rename it a. I know I'm solving for y, so I get y equals plus or minus square root of x squared plus 2c. And it's right around here where the book will rename it. Okay, so I'm going to use k. And this is my general solution. And you're like, well, why are you bothering renaming it? It's just, you know, like I said, we're talking about minimizing pen strokes. Why should I call it 2c when I can call it k, right? Why should I use 2 characters when I can use a single character? So let's look at that general solution. Let's look at that slope field, right? Everybody with me here on the slope fields? Charlie's using it. David's using it. So in my slope field, I want to put in that x over y, right? X divided by y. And at this point, I'm going to stop and just have you notice something about my slope field, okay? Oops. Sorry. It's freaking out on me. X divided by y. Cool. It's looking like the cooling towers. You see it? The cooling towers of the hyperbola of the nuclear power plant. So there's, right, this is a half of a hyperbola. Or the shadow, if you look at if you have a lamp in your living room and you turn on the light, that stuff that's coming out of the top, you know, the cast of the shadow on the wall from the shade, you'll see a hyperbola, top half and bottom half coming out. So why not? Let's keep it nice and simple for us. Let's make the initial value 0, 1. Right? Let's just keep it simple as much as we can. So let's say, so there's our general solution. Find the initial value. Value, can you spell, Robert? Yes, value. Solution if y of 0 is 1, right? If I plug in x as 0 and I get out of y is 1, right? So I get 1 equals plus or minus square root of 0 squared plus k. And so I get 1 equals plus or minus square root of k. What's my only possibility for k there? Well, it's clear it's positive, right? Clear it's positive. Or I could just solve this for k squared both sides. So k is 1, right? K is 1. So y equals square root of x squared plus 1. Do I need the plus or minus? No. So that plus or minus got me to, right, remember this was the general family of solutions. I'm trying to figure out the initial value solution. Once I get to k, I need the plus or minus to get me to k. I think so. So let's go to now, not to slope fields, but to our Desmos, and then graph that solution I got, right? What was that? Square root of x squared plus 1. And there it is. And so there could be some confusion with the pluses and minuses and all of that, but then, you know, once you start graphing things, you'll be convinced with what you have. Not bad, right? Am I right? Okay, I want to talk about the slope field. So in this particular problem, it's easy to generate the slope field. I want to see what that is. So we just found out how to do an initial value problem. I'll show you. Before I go to the slope field, I'll show you the one I had on my last semester's final. I was really debating on putting this on your midterm for Thursday, but now I can't do it. But y prime x squared square root of 1 minus x squared equals 1 is my, I asked you students to solve this problem. In fact, I had it as, what did I have it as? No, that's what I had it as. Something like that. It doesn't matter. But then, of course, dy equals 1 over x squared square root of 1 minus x squared dx. Right? And so it's, what kind of problem is it?
Trig sub.
Trig sub. Yeah. So it looks like I have a leg and a hypotenuse of 1. So the integral of dy equals the integral of 1 over x squared square roots of 1 minus x squared dx. And I'm going to do a trig sub here. So what is x is what? Sine. Dx is cosine. D theta, right? And square root is what? Cosine? Oh, it's probably an x to the 4th. Okay, but that's all right. So anyway, what do I get? I get y equals the square root of, sorry, the integral of sine theta cos theta d theta over cos theta. Too easy, huh? And the antiderivative of sine is what? Negative cosine? And so the negative cosine is what? It's 1 minus, so c minus the square root of 1 minus x squared. And there's my general solution. I think I gave something more difficult than that, but I did promise them that the midterm was too hard, so I would make the final easy. And I did. I made the final easy last semester. Okay, I want to go to slope fields if I can move on, but you gotta let me know. You gotta control me. I feel a little hopped up today, so because my
Professor?
Yes, Ash.
Why does the square root of 1 minus x squared equals cosine?
Oh, did I do everything wrong there? I did everything wrong there. I'm sorry. I did everything wrong there. I realize it now. I got all of this right. I'm sorry. What's wrong with me today? I got the integral of dy. On the other side, x squared is sine, so I've got a sine squared downstairs, right? And then upstairs I have a cos theta d theta, and then I have another, that's it. I'm sorry. Thank you, Ash. So those cosines cancel, and I get y equals the antiderivative of cosecant squared. That's the one I gave last semester. I thought that looked a little bit too easy. And what's the antiderivative of cosecant squared?
Negative cotangent.
Nice. So y equals negative cotan of theta plus c. And then the cotan is going to give me what? Square root of, yeah. So y equals negative square root of 1 minus x squared over x, all plus c. There it is. Sorry about that. Thank you, Ash, for pointing out my mistake by saying, Robert, what the hell did you do there? I'm just so happy everyone's leaving the apartment. They're gone. Is that bad? Does anybody else feel the way I do, or am I just a horrible person?
No, I can relate.
Me as well.
Thank you. You're all making me feel better, but the rest of the class is going, you're all evil. It's usually why I hate teaching 3-day-a-week classes. I don't even like seeing my family 3 days a week, let alone students. But now we're 4-day-a-week, right? All right, let me talk about slope fields, okay? Let me talk about slope fields because they're so easy. I mean, we're really close to being done with this, and then talk about Euler's method, and then we have very little to do next time. We got separable equation by parts. I'm sorry, by U sub, and then orthogonal families, which are cool and fun and beautiful. But you're talking to a nerd. So I want to look at a slope field now, okay? And I'm going to generate a slope field, and this is something you don't have to do, but I want you to understand what they are. Because it's like kindergarten, this kind of problem. So what is a slope field? So I've got what y prime is, what did I have, x over y, right? And so I want to generate a bunch of values for x over y, and notice that this is the slope, right? So if I'm looking at my grid, and I'm doing integer values everywhere, right? Integer values everywhere. And I usually just work with the first quadrant, it makes it easier. But when x is 1 and y is 1, right? When x and y are both 1, y prime is going to be 1 divided by 1, which is 1. So I'm putting a slope of 1 right on that tick mark. And that's a guide for my water, right? It's a blocker for my water. Does that make sense? It's really that simple. So give me another. What point do you want to look at? Let's try and find that initial value path that we had. What about at 0, 1/2, right? Or 0. How about 0, 1 even? I like just to keep it. So if x is 0 and y is 1, I'm sorry. Yeah, if x is 0 and y is 1, sure. I have my slope field is 0, is x over y, that's 0 over 1, that's 0. So at 0, 1, I have this slope, right? And you can always see it's catching my my kind of parabola, right? Remember my initial value solution or my general solution? You can see it's already kind of catching that. So I guess what should I try next at 1, 1, right? At negative 1, negative 1, negative 1, positive 1. Right? Is this making sense? I'm just picking integer values, plugging them into my differential equation, and then drawing the slope at that point. That's all slope field is. So this one I have negative 1 over 1, which is negative 1. And I'm drawing that slope of negative 1. And you can see that thing is catching that curve I just had before. Right? It's guiding the water flow kind of thing. It's that simple. Really, really, really is that simple. So if I go back to that, is everyone with me? Anybody? Nice.
What do you, if it's undefined, do you do a vertical line?
Exactly. In fact, if it's a 0 over 0, I do a vertical and a horizontal. Right? If I get a numerator 0, I get a horizontal tangent. If I get a denominator 0, I get a vertical tangent. So when I have that 0 over 0, that's a really rare case. But let's look at our slope field that GeoGebra generated for us, right? And so look at 0, 0. It doesn't know what to do, but I'm saying there's very likely a horizontal and a vertical here. But of course, it's not in my domain anyway, right? So I've got to put in things in my domain for x and y. But look at a particular point here. Let's see if I can find one at 2, 2. Here's the ballerina point, right? Right there. Can you see the hand on the screen there? Can you see the hand on my slope field there? It's pointing to the ballerina point, which is a joke 2, 2. Right, so at 2, 2, I'm doing 2 divided by 2 is 1. So you can see anywhere x and y are equal, you see that whole slope of 1 there. That whole slope of 1. And it's fun to put these things at different spots so that you can see the different values, right? So now I'm looking at the family, right? Does that make sense? I'm looking at the whole family of curves here. This is the general solution. It's showing me where any of those initial values would be, right? That it would generate all of these possible solutions. Super easy, right? And of course, right, if we're trying to find this future value, I can certainly plug in now, right? So so what was my initial value? I forgot already. Y equals square root of x squared plus 1, right? So now that I've got this initial value problem answered, I know y of 0 was 1. The question is, how do I find y of 1 now? Well, that's simple. Just plug in, right? I get 1 squared plus 1. So it's moving to square root of 2. When x is 1, I'm getting a height of square root of 2 out of this solution. And remember, we're trying to predict a future value of how things are going to change. Are we going to get to the moon? Are we going to get out of the Earth's orbit? You know, that type of thing. It's not all space flight. It will be, in bio, it'll be, you know, how many cells survived, how many, you know, that type of thing. The amount of a drug in a system later on, that and all of that type of thing. In engineering, I don't know. I'll let your DiffyQs teacher teach you the applications to engineering, but I mean, it's been a while since I've taken the class, so give me 1 second. I'm going to check on something. You okay? You okay? Sorry, babe. I can help in about 20 minutes. Okay? I can help in 20 minutes. We'll just get a new sofa. We'll get a new sofa. Okay. Sorry, babe. Okay, I'm sorry about that. I'm back. So I want to start Euler's method today. I don't want to do the whole thing, okay? So I'll get back to it. We're going to be, so Tuesday we're going to be solving more solutions, right? Some more general solutions, initial value solutions, plugging them into slope fields, that type of thing, making sure we got a correct thing. We'll do a couple more difficult ones as well. But once we find a solution, okay, once we find a solution, we can make a future value. But what if we can't find the solution is what we're talking about here. And so what we're talking about now in this particular section, and this is 7.2, Euler's method. Given an initial value, find an estimated future value. And so if I had a dy dx, like I had before, x over y, right? And I could draw that slope field, right? I could draw that slope field, and I could see around where, so if my initial value was 0, 1, I could kind of predict where y of 1 would be, right? It looks like here. But I don't know how accurate I would be, right? And so we're going to use Euler's method to figure this out, right? And we already know the actual answer is square root of 2, right? About 1.4. Let's see what Euler's method does for us, how close it gets us, right? So because I haven't had calculators on tests lately, I have not been giving this on an exam. But I do like finding an initial value problem type of thing. So right now my instinct says I'm not going to do this because it doesn't make sense to do it by hand. It's like, you know, you would use a computer program to do it. So, but I just want us to see it, okay, and see how close it gets. So my Euler's method here is in 7.2. Excuse me a second. Elaine, will you just stop until I finish, please? I can cancel class, but you want me to stop class? Hello? Okay, I'll stop class. I'm sorry, I need to go help my girlfriend. So we're going to stop here today, but if you can give me about 20 minutes, I'll be back for some office hours. But we'll just stop class here. I'll finish this tomorrow. No problem finishing it all tomorrow. Okay?
Okay. Thank you, Professor.
Yep.
Thank you.
Thank you, Steve.
Thank you.
You're welcome.
Thank you.